The purpose of this list is to juxtapose the capabilities of the Anova and the regression methods. So it's important to have just this broad understanding of when you would use which technique, and so that's what this little illustration is all about. So I have this kind of data. So let's say you're doing a research study of some kind, and you say, I have this type of data, this nature of data, and I'm asking this particular question with it. And so given that information, which stat technique is going to be the best one to use, and the ones that make sense when we're trying to present that study to the consumers of our research. So just to give you an idea, I've listed here 7 different tasks, and then noted on the columns to the right which technique is best for that. And as you can see, regression overall holds up as a possibility for analyzing data of this nature, of these different tasks, and it holds up more so than Anova does. So what I would say just overall is that Anova is great. It's been used historically a lot more than regression, just because the math behind it is less complicated. I know that's hard to imagine because you did Anova last quarter, and it can be kind of complex to calculate by hand. However, it can be done much easier than regression, because regression behind the scenes requires extensive matrix algebra to calculate, whereas Anova does not. So matrix algebra is notoriously difficult to do by hand, of course. And so before computing capabilities, back several years ago, regression just wasn't an option. So that really put a limitation on the kinds of research questions that people could ask. So Anova was done for a long time before regression ever came on the scene, and then we were able to get technology up to the place where we could do very complex analyses, and that's when regression took off. And I would say into the future, what I'm seeing trend-wise is that even regression now is becoming it's becoming less used in and of itself. Most of the time now regression is used, even though it's the foundation of everything. There are much more complex capabilities that are built on top of it. So we have structural equation modeling, which you'll learn next quarter, and we have multi-level modeling, also you'll learn next quarter. And those techniques require a pretty extensive computing capability, which thankfully we have now access to. There are various programs that do it even better than SPSS, I would say, some of these techniques. You'll learn AMOS next quarter, but just know that there are other platforms available that are much more powerful and probably more expensive, most of them. There's Stata, which I know is used a lot. There's SAS, which is kind of the, I would say, one of the oldest and most beloved programs for complex stat analyses, which you probably won't even learn in this program unless you really want to. But SAS has been widely used, and it's extremely powerful. If you know that platform, I would say, which I don't even know that platform, but if you do know that platform, you can do just a lot of flexible techniques. Anyway, so that's probably more information than you need to know, but I just want to give you the background for Anova versus regression, and just know that Anova is a pretty specialized technique that almost any stat program can do, which is great. But you probably won't use it much in your research. I would say one way Anova you'll probably use the most, depending on your question. But like if you're trying to compare means across 3 or 4 different ethnic groups, for example, one way is really nice for that. But you could also do that in regression, which we'll talk about. All right, so let's get to the tasks at hand here. So the first one is when you have unequal cell ends. This can be an issue in Anova, as I'm sure you know. There are some corrections for that, and some ways that field tells you how to deal with that. And that's fine. Those are for reference. You never have to know those like for an exam or something. But just know that unequal ends are an issue in Anova more so than in regression. So that kind of takes care of that issue when we use regression. The second one, analyzing data with categorical predictors. Anova does this extremely well. So if you have two, let's say, variables that are categorical, and you're attempting to understand how they interact somehow, let's say you have a 2x2 where you have a manipulation where you are putting somebody under stress, or you're making, one comes to mind actually. It's a social psych research study in which they had a room with a weapon, not a real one, but it looked real, and then they had a room with a tennis racket. And before they sent the participants to that room to think about something, they either angered the participant or they did not. And so that is a 2x2 study where you have one manipulation is provoking the participant, and the other is which room they sat in. Did they sit in the one with the weapon? And just FYI, what the researchers found is that those who were angered and saw the weapon were behaved more aggressively in a later task. And so the evidence there, or the inference that they made, was that individuals who are provoked will become even more angry when they just see an assault weapon. Interestingly, those results did not extend to a hunting rifle. So a follow-on study was conducted, and the participants who were provoked were only more angered when the weapon was an assault weapon, or like some kind of handgun, rather than a hunting weapon. So anyway, that's an example of a 2x2, and that means both your IVs are categorical, a 0-1 case, and in that particular case, an Anova is the best way to analyze that data, as you learned last quarter. So if you have that case, you would use Anova, but regression can also handle that kind of case. I just don't recommend regression. It's just not the easiest way. So there you have it. If you did have a couple of covariates, you can do an ANCOVA in that case. I don't know if you've learned about that, but it is a possibility. And if you ever need to do that for dissertation, if you have like a 2x2 case and then you have some covariates that you're concerned about controlling for other things, like the person's age or other, attributes of the person, you can do an ANCOVA, pardon me, and that is referenced in Field if you ever need to know that. Okay, moving on. Number 3, analyzing data with continuous predictors. Anova cannot do this. So continuous predictors are things like someone's age, somebody indicating 1 to 7 on a particular Likert scale survey. Anova cannot handle that kind of those kind of IVs, and so you would want to use regression. Number 4, assessing the amount of variance in an outcome that's due to a combination of predictors. So what we want to do is parse out variance. We want to understand above and beyond this predictor, does this other predictor contribute to the DV? So we would want to know if our intervention, whatever it is, will move the dial on the outcome of interest above and beyond a person's pre-existing conditions. And so the only way to answer that question is with regression. Anova cannot answer that. Number 5, determine the extent to which predictors are correlated with each other. So Anova can't account for this idea that predictors are associated with one another, and so we want to understand how each one uniquely contributes to a DV of interest. So that's related to number 4. Number 6, analyze data with dichotomous Dvs. So in your research, I would say this is probably less frequent, but you may have a case where you have a DV that is only a 0-1 or a yes-no, or the presence or an absence of some kind of attribute. So some examples of this would be, I'm trying to predict someone's suicide attempt. So we would say that, 0 means they don't have a suicide attempt and one is that they did. And so that would be a special case of regression. Anova certainly can't handle this case, but a special kind of regression can, and it's called logistic regression, and we will learn that later this quarter. Other examples of a dichotomous DV would be things like a guilty-innocent verdict. So if you need to do research on legal psychology and you want to know the likelihood that a jury will find guilty versus not guilty, then you would use logistic regression. Note that if you changed it on a scale, let's say you were doing a mock jury and you had the jury say the probability that they would convict on a 1 to 7 scale, that puts the DV back in the continuous category, and we would not have to use logistic regression. We would just use regular regression, which most of the time, 90% of this class will be continuous DVs, not dichotomous. But I just want to teach you briefly at the end of this course some cases of logistic regression in case you have to use it for a dissertation or a future investigation. Note that in field you have references to logistic regression and how to do it, and you also have access to how to do multinomial regression, which is a categorical DV with more than 2 categories. So you would want to predict the likelihood that someone would end up in a certain group of some kind. So I can't think of an example of that right now, but it's very rarely used, I would say, at least in my field. But it is available to you in case you need it in field, with very detailed instructions how to do it in SPSS, so it's extremely helpful. All right, last one, modeling curvilinear relationships, which we will do in this class. And this is the idea that there's like this curvilinear relationship between one I like to use that's kind of funny is the illustration of glasses of wine per day. You know how people say a glass of wine or 2 a day is great for health. And so people are like, well, if 1 glass is good, then 5 glasses must be better. Well, that's not the case, because probably there's a diminishing return to this, such that as we move past 3 or 4 glasses, we're getting into a health detriment category. And this is a perfect example of a curvilinear relationship, specifically probably an inverse U shape, which we'll talk about later. That means that there's a positive relationship to start with between glasses of wine per day and health, such that up to 1 or 2 you're good, and then as you get past 2 you start to have this negative association. So it's not positive association the whole way through. So more is not always better. And Anova cannot handle this, but regression certainly can. And it's just so in conclusion, I would say just the takeaway is that regression is a much more flexible technique, and you can do a lot more with it to answer the questions that you need to answer in your research.